Okay, so balancing chemical equations is what we do when we're trying to figure out exactly how much of each thing reacts and how much of our products we're going to get. So for example, Janica was kind of concerned earlier on when I was showing these reactions, and rightly so. Some of this looks kind of funny. For instance, if we're looking at this first synthesis reaction, it looks like I'm saying that I have one magnesium atom reacting with one oxygen molecule consisting of two oxygen atoms. And that makes one magnesium oxide molecule, which consists of one magnesium atom and one oxygen atom. And the problem with saying that is that I have two oxygen atoms on the left-hand side and one on the right-hand side. It makes it look, if I leave the reaction like this, it makes it look like one of my oxygens disappeared, like maybe it was destroyed in the chemical reaction. Can atoms be destroyed by chemical reactions? No, they can't. That was one of our fundamental tenets of the atomic theory you guys memorized for the first exam, right? Atoms are not created or destroyed by chemical reactions. So even if it looks like I've lost one, I really cannot have lost one. So what we do essentially at this point is we have to balance it. And before we do that, let me emphasize it's important that my reaction reads this way. I can't have my reaction make this product. That would be convenient, right? Because then I would be using one magnesium and two oxygens. But I can't do that because you know and I know magnesium's in group 2, it makes a +2 charge. Oxygen's in group 6, it makes a -2 charge. This would not be balanced for charges. It wouldn't make a compound. It wouldn't be neutral. You can't do that, okay? The reason I have one magnesium and one oxygen is because that's what makes the charges balanced. And so that's the right formula for my ionic compound. I just have to make the numbers of atoms match. So that's what balancing equations is about. It's a tool that helps us determine how many reactant molecules will react to form how many product molecules. And we're going to balance the equation by systematically adding molecules or atoms on each side to balance them, like we've got scales, and we just need to make sure we have the same numbers of oxygen atoms on both sides, that they're balanced, and the same numbers of magnesium atoms on both sides. So the way we do this is we're going to put a number out in front of the atoms of the molecules. So for instance, you can see I've got one magnesium on the left, one magnesium on the right. Those appear to be balanced. Two oxygen atoms on the left, only one on the right. So if I put a 2 here and say, all right, well, this reaction must make 2 magnesium oxide molecules because that would give me 2 oxygen atoms, and now my oxygen atoms are balanced. So this number here is called the coefficient. And the reason that I have to put it there is because, again, I can't put the 2 there because that would change the formula of my molecule. That's not legal. I have to put it out in front and basically say I'm making 2 of this whole thing. Okay. Now that gives us another problem, which I think Rob is about to tell me about. It does. It does. Good observation, Robin. When I put the 2 out in front, that tells me I have 2 oxygens, so yes, awesome, they're balanced. But it also tells me that I have 2 magnesiums, and so now my magnesiums, which were formerly balanced, are not balanced anymore. What would I have to do to balance my magnesium atoms now that I put the coefficient of 2 in front of my magnesium oxide? Yes. Put a coefficient of 2 in front of the magnesium on the left-hand side, and now my equation shows 2 magnesium atoms on both sides and 2 oxygen atoms on both sides. So since I have the same numbers and types of all atoms on both sides, this equation is balanced. Balanced. Yay! Let's try this one. Balancing chemical equations is, there's not like one formula systematic way that I would recommend doing it, because with different types of chemical reactions, there's going to be kind of different ways of doing it. I'm going to generally say eyeball it and give you one recommendation, and that is if you have an element that's all by itself or an element that's in more than two places, right? Like I've got oxygen in everything. Do that element last. That's my number one recommendation. So looking at this, I have oxygen in everything. I'd like to balance it last. Additionally, I have oxygen all by itself right here. Again, that's going to help me to want to balance the oxygen last, because I can make this anything I want without messing up all of the other atoms in the reaction, if that makes sense. Okay, so follow me here. I have one sulfur on the left-hand side, one sulfur on the right-hand side, so they appear to be balanced. Now, these two compounds containing sulfur are balanced against each other, so let's check that out. Here I have what appear to be a total of 4 oxygen atoms on the left and only 3 on the right. Now, before you say that, I'm going to recommend you look at this from a different perspective. These two are balanced against each other, the SO2 and the SO3. Instead of saying that this is worth 2 as if I already have a 1 out in front, I'm going to say, no, I don't have anything out in front. What I have here is a question mark because I haven't decided what I need it to be to have it be balanced. So I could say I have 2 oxygen atoms here and 3 oxygen atoms here. So I need this to represent how many oxygen atoms to make sure they're balanced. 2 plus what equals 3? 1, perfect. I need this to represent 1 oxygen atom. That does give me a little bit of a problem because, as it turns out, these come in pairs. What would I put in front of that? What kind of a coefficient would give me only 1 oxygen atom? Or in other words, what times 2 equals 1? Philip's exactly right. If I put a 1/2 here, then 1/2 times 2 will equal 1. So now I've got 1 sulfur atom on the left, 1 on the right. 2 plus 1 oxygen atoms on the left, 3 oxygen atoms on the right. This is perfectly balanced. Here's my second recommendation. Don't be afraid to use fractions temporarily. You guys may have taken a chemistry class in the past where they said, you can't use fractions, it's not allowed. And that's fine, but you can use them temporarily. And you see how we did that, okay? Where we just looked at this and said, what does this need to be? This is a stopping point. This is perfectly balanced, but it does have a fraction. What would be the easiest way of getting rid of the fraction, but making sure that everything remains balanced? Double the equation. Excellent. If I multiply everything in here by 2, it'll still stay balanced because I'm multiplying everything by the same number. That would get rid of my fraction here. So in so doing, then multiply the first one by 2, that'll become 2. When I multiply 1/2 by 2, it just becomes 1. And then when I multiply the last one by 2, it becomes 2. So now we can just review it and ensure that our reaction is indeed balanced. 2 sulfur atoms on the left, 2 sulfur atoms on the right. Excellent. 2 times 2, that's 4 oxygens plus 2 oxygens gives me 6 oxygen atoms on the left. And 2 times 3 gives me 6 oxygen atoms on the right. Hooray, it's balanced. Okay. All right. You guys want me to do a few more, I think. Am I right? For sure. Okay. Again, so tips number 1 and tips number 2. Let's see, what did we say? Number 1, if an element is in 3 or more places, do it last. Also, if an element is by itself, it helps to do it last too. Number 3, we said if, don't be afraid of fractions. It's actually much easier to stop on a fraction and then just double the whole thing than it would be to try to eyeball it into a different place. Okay, you could spend a lot of time trying to eyeball it, or you could just assign it a fraction and then double the whole thing. Okay, so next here I have FeCl3 going to form Fe and Cl2. And both Fe and Cl2 are by themselves, so we do have, it doesn't really matter which one we choose to do. So I'll just kind of go from left to right. I've got 1 iron on the left, I've got 1 iron on the right, looks good. I've got 3 chlorines on the left and only 2 on the right. Uh-oh, what do I need to do here? What would be an easy way to balance my chlorines? Add 1 on the right. Okay, so if looks like I've got just 3 versus 2. If I make this 2, then I got 3 versus 4. That doesn't quite get me where I want, but you do recognize I'm going to need more on the right. Or how could you add just 1? No, you're fine. You did the exact right thing in saying I need more chlorines on the right-hand side. Okay, Travis says, let's try to find the common multiple. That's a good idea. This was like when we were trying to balance charges and one had a charge of +3, one had a charge of -2, right? Oh, Philip's on top of it. Okay. So if you find the common multiple, you'd say, well, 3 and 6 and 2 have a common multiple of 6. So if I put the 3 in front of the 2 and the 2 in front of the 3, then I end up with 6 chlorines on the left, 6 chlorines on the right, and they're balanced. But note that that unbalances your iron. Don't be afraid of that. It's really easy to go back and say, okay, I've got 2 of those. Okay, so there's one way to look at it, is to find the lowest common multiple. Another way to look at it would be, Shauna Meredith said, I just need 1 more of these. I need this to represent 3 chlorines. If I make this 3 halves, then that's totally balanced, and it represents 3 chlorines, and the whole thing's balanced. Then I could see that I just need to go through and multiply everything by 2. And if I did that, I would get 2, 2, and 3. Just the same way as if I looked for the lowest common multiple. Both of those processes work. Both of those will work just fine. Okay, let's try this guy. HNO3 goes to form H2O and N2O5. What am I going to balance last? The oxygen. Oxygen's everywhere. That's terrible. I don't want to deal with oxygens because if I change it on one thing, then I end up changing the hydrogens or the nitrogen. So I'm just not even going to worry about the oxygens till the end. So if we do the hydrogens first and the nitrogens, we can see, let's see, 1 hydrogen on the left, 2 on the right. So if I put a 2 in front of there, that will balance my hydrogen atoms. Now putting a 2 there gives me 2 nitrogen atoms. And here I appear to have 2 nitrogen atoms, so my nitrogen atoms are balanced. Okay, hydrogens and nitrogens both balanced. Now I'm going to look at the oxygens and hope that they fall into place because everything else looks good. So 2 molecules, which each have 3 oxygen atoms, gives me 6. On the right, I have 1 oxygen atom here and 5 there. Hey, look, it adds up to 6. That just fell into place. That was a lot easier than it looked like it was going to be on the outset, wasn't it? What you'll find is that if I've written the reaction properly, they're all possible to balance. And you might just only have to balance one or two different things, and you'll find that the rest of that falls into place. A little bit of faith. It's going to work, I promise. Everybody agree with this one? Does that look balanced to you? Yeah, excellent. Okay, let's continue. Let's do a few more here. Doesn't hurt to have lots of practice. Combustion reactions, what are you going to balance last? Number one recommendation for combustion reactions. Yes, exactly, Philip. We're going to do oxygen last for two reasons. First of all, it could be in 3 or even 4 different places. Gross. We want to do it last. Second of all, over here, it's all by itself. I can make that number anything I want to, and it won't upset the balance of my other elements that I'm working with. So for combustion reactions, strongly recommend always do your oxygen last, very, very last, okay? Other than that, just go from left to right. Let's do this second one first. So C4H10O, we have 4 carbon atoms on the left. So putting a 4 in front of that CO2 will give me 4 carbon atoms on the right. Balancing our hydrogens, I appear to have 10 hydrogen atoms on the left. So since these come in pairs, I'm going to need 5 water molecules on the right to give me a total of 10 hydrogen atoms. Everybody agree with my assessment of the carbon and hydrogen balancing? This is with, if there's nothing listed, it's a 1. I'll put the 1 there, but you don't need it. Everybody following so far? It's not completely balanced. I haven't touched the oxygen. I'm just confirming that my carbons and hydrogens work. Excellent. Okay. Now to do the oxygens, I'm going to say, here I have 4 times 2 is 8, plus 5. I have a total of 13 oxygen atoms. On the left, I have balanced these ones. I don't want that to change, so I'm going to make this a 1. And then this needs to be what? I'm not assigning it anything. I haven't assigned it anything yet. It's not 2. It's not anything. How many what do I need to put here to make this equal a number that's going to make that balanced? Yay, 6. Because 6 times the 2 oxygen atoms would give me 12. And 1 plus 12 is going to give me 13. And my oxygens are balanced. See how much easier that was to do the oxygen? I say easier, but without doing it the other way, you might not see that. But maybe it was easier than you thought it would be to do the oxygen first. I just want to try to clean this up a little bit so it's easy to see. Everything really kind of falls into place if you just do one step at a time. All right, let's do the first one here. If I say I've got one of these, that gives me 8 carbon atoms. So I better put an 8 in front of my CO2. 18 hydrogen atoms. So since they come in pairs, I'm going to put a 9 in front of the H2O. Now, what do I need to put here to balance out my oxygen atoms? We look here, we've got 16 oxygen atoms. And here I've got 9, so I have a total of 25 on the right side. This needs to represent all 25, but they come in pairs. What should I make that? Or in other words, what times 2 is going to give me 25? Philip Martin says 12 and a half. Perfect. Or 25 halves, right? I don't even have to do the math and tell me how much 25 halves is. because as soon as I know it's going to be a fraction, I know that that's only a temporary stopping point. This is balanced. Everybody agree? I have the same number of carbon, hydrogen, and oxygen atoms on both sides. Brooks agrees. She says it looks balanced. Phillips agrees. Says it looks balanced. Okay. This was a temporary stopping point. What do we do now? Double the equation. Excellent, because it's balanced, but we don't want that half. So that 1 becomes a 2. And 25 halves will become what? Just 25. Excellent. And that 8 becomes a what? 16. Excellent. And the 9 becomes 18. Now, don't be uncomfortable with these big numbers. 16, 18, 25. That's what you get with combustion sometimes. Turns out burning gas takes up a lot of oxygen and makes a lot of carbon dioxide. There's a reason that combustion engines release a lot of carbon dioxide in the air, as you can see, because it doesn't take very many octane molecules to make a lot of carbon dioxide molecules. Okay. All right. That's combustion. So again, recommendations for combustion: always do oxygen last and don't be afraid of fractions. Okay. Finally, not finally, we've got a little bit longer to go. Single displacement and double displacement. I think you'll find that despite looking more complicated, they end up being actually a little bit easier than the former ones that we just looked at. So iron, H2SO4 makes iron sulfate and hydrogen. Any recommendations on what we need to do to that to make it balanced? While I'm cleaning up these others. Yeah, that was easy. Look at that. I have one iron atom on the left and one iron atom on the right, pardon. I have 2 hydrogen atoms on the left and I have 2 hydrogen atoms on the right. And I have 1 sulfur atom on the left, 1 sulfur atom on the right, 4 oxygen atoms on the left, 4 oxygen atoms on the right. Everybody agree that looks completely balanced? That was easy. Sometimes it is. That's not always easy, but sometimes it is. This brings me to my next recommendation, which is sometimes you'll see polyatomic ions, the same one on the left and the right. If you do that almost all the time, vast majority of cases, you don't need to balance each individual sulfur and oxygen. You could just balance the entire polyatomic ion as a whole. So I could say 1 iron atom, 2 hydrogen atoms, 2 hydrogen atoms, 1 sulfate ion, 1 sulfate ion. You guys following what I did there? To just balance that whole cluster because it's conserved on both sides. So here we go, recommendation 4. Balance whole clusters of polyatomic ions. Now, there are some cases where you can't do that. It'll be clear because you won't have the same polyatomic ion on both sides. Okay. This only works if you have a sulfate on the left and a sulfate on the right, then you can just balance the whole thing. So for instance, here I've got a nitrate on the left and a nitrate on the right. So instead of balancing individual nitrogen and oxygen atoms, I could just balance my nitrates. Okay. So help me out here. What do I need to do to balance this single displacement reaction? Yeah, Travis, if you're looking at the start, it looks like you've got one magnesium on each side and one silver on each side, but here you appear to have now 2 nitrates. That's going to be a problem because I only have 1 here. So let me put a 2 here. That'll fix my nitrates. Now my nitrates are balanced. Does that cause me any other problems? Does that give me more work? Or am I done? Yes, perfect, Brooks. By putting the 2 in front of the silver nitrate to balance the nitrates, now my silvers aren't balanced anymore. So since I've got 2 silver atoms here, I'll need 2 there. Perfect. What about now? I'm not sure what you're asking, Philip. If I ask you to predict the product, and you know that it's going to form elemental silver, then it will be important to know whether that elemental silver is a diatomic species, like the hydrogen or the nitrogen, or if it's a single species. But I'm not actually going to have you predict products for single displacement reactions. But yes, yeah. In fact, Philip, here's a good example of the one that just came above. When hydrogen forms, elemental hydrogen, it's H2 instead of saying 2 H's. But yeah, I'm not going to, at least for the single displacements, you won't have to predict that. The only ones where I'm going to say predict the products would be the double displacements and the combustions. So at least for the moment, you don't need to worry about that necessarily. Unless I say, like, balance the equation and I read it off to you like iron plus sulfuric acid forms iron 2 sulfate plus hydrogen, then you would need to know, oh, okay, hydrogen's going to come as H2. I think that answered. Okay, excellent. All right, everybody feel good about this one? Are we done, or did I mess something else up when I put the 2 in front of the silver? Yes, Robin, these 2 with stars. I might ask you to predict the products. Like I said, what are the products when sugar combines with oxygen in a combustion reaction? You'd have to say carbon dioxide and water because that's the same for every combustion reaction. Or if I said, what are the products when lead nitrate combines with sodium carbonate? You have to say, oh, it's double displacement. So because the cation always goes with the anion, I'm going to be lead and carbonate and the sodium with the nitrate. You guys can do that. Okay, so this one's balanced. Help me balance this double displacement, and then we'll look at the in-class activity sheet really quickly. Tell me what we need to do here. Again, you can just kind of read it left to right. Evaluate the leads, evaluate the nitrates, evaluate the sodiums, evaluate the carbonates. You guys tell me, if I do that, what will my coefficients be? You can just give me 4 numbers for those 4 coefficients. Okay, Robin says, I'm going to need 2 of these. Robin and Brooks agree. Everybody else agree with that? Yeah, that's all you need. If you looked at it, each individual's, you've got 1 lead, that's balanced. 2 nitrates, okay, that's where you say, okay, I need 2 nitrates, so I'm going to put that out in front. Here I've got 2 sodium atoms. Hey, look, putting the 2 there solved your sodiums as well. And 1 carbonate, Excellent. Excellent. Okay, last one. You guys tell me, what do I need to put there? Looks like you guys are picking it up. Well, Kylie's on top of it. Since I've got 2 potassiums and 2 chlorines, I'm going to need 2 KCl's, and that does it. I have 1 sulfate, 1 calcium. Everybody agree? Does that look good? Excellent. Okay. So let's look at our ICA 5.1. So this whole section 1, we've already classified. I also want you to balance all of these before we come to class on Wednesday. That looks like a lot of work, but it should only take you less than a half an hour of trying. And I'm going to recommend, when you balance, here's my recommendation, go in reverse. In other words, start here, balance this, and move up. Once you're done with the second column, then start here and move up. So I want you to do these backwards, not the balancing itself backwards, but the order in which you do them backwards, because there are more single and double displacements in this column, and they're a little bit easier, and there's more synthesis and combustion on this column. They're a little bit harder. So I want you to work on some of the easier ones to get your feet wet before you start on some of the harder ones, but I want you to try them all. Is that fair? Are there any that you guys want me to do before we move on? We've done a lot of examples, but I don't mind doing one or two more here. Philip's typing, so I'm waiting for him. Oh, there we go. You are not lost. We're just not there yet. That's the next thing to talk about, Philip. So if you guys are feeling good about combustion, we'll move right on to precipitation and acids and bases. And if we're really lucky, we'll get to oxidation reduction today, but we might have to do that on Wednesday. You're not lost, Philip. We're just not there yet. Okay, so if you guys feel pretty good about this, or apparently good enough that you don't have any questions for me, then we'll move on.